The following content is provided.
Given any particular setting in the environment, you have a measuring device that can produce many different outcomes. And you observe the final outcome of out of your measuring device, and you're trying to guess which outcomes. So think of trivial half-line probabilities that you get after you do some inference based on the information that you have available. Now, the base rule we derive.
So we had like so we had that, A like follows B. This is like cause and effect. So this is like there's some, what would you call this? There's some not outcome. There's some, it's not an outcome, not an event. There's some, what do you call it? I don't know, there's something and it like causes something else versus you observe the state of the world and you're trying to infer what you observe some data and you try to infer what the state of the environment was to cause that inference. Let's see what.
The following content is provided on
Conditioning. And we model a scenario, and so a scenario occurs.
Scenario.
And that may cause B to happen or may not cause it to happen. So this is a cause-effect model. And it's modeled using probabilities such as probability of B given AI. And what we want to do is inference where we're told that B occurs, and we want to infer whether AI also occurred or not. And the appropriate probabilities for that are the conditional probabilities that A occurred given that B occurred. So we're starting with a causal model, derived it, and it's a trivial half-line calculation, but it under a certain situation. You can think of these probabilities as describing a causal model of a certain situation, whereas these are the probability.
It's kind of like two things to really be able to like write out this Bayes rule thing here. First, it's kind of like you need to be able to go from like the probability of A given B is equal to, well, it's like, so B occurred. So we're in this new like universe where just B occurred. And then we're just interested in the part of A that overlaps with B. So it's kind of like step one that you need to be able to do to kind of get to the full thing. You've got to kind of relate a conditional to a intersection essentially. And now step two is, so what's the probability of A intersect B? This is equal to, say, like the probability of A times the probability of B given A. So to kind of get from here to here, you got to say, almost kind of like, okay, the probability of A given B. It's kind of like A and B, and you're kind of just like in this world now, just given B. So that's where the denominator comes from. But you're just interested in the A given B isn't this. This is just the probability of B. You're interested in the amount of A that intersects with B over that whole area. So that's where that is. So that's kind of this picture. But then to get from, yeah, that's kind of like, yeah, that is this picture. It's like this is like the numerator and like this is the denominator. But now you have the probability of A intersect B, and we're kind of just like starting with the intersection here. And we're saying, what is this in terms of conditional probabilities? Well, it's equal to basically, you kind of start with A, and then we're going to like crunch it down. So it's like the probability of A times probability of A given A. We're multiplying it by the proportion that's also inside of A. That's B. Yeah, it's kind of, I guess it's basically that, yeah.
That you get after you do some inference based on the information that you have available. Now, the Bayes rule, we derived it, and it's a trivial half-line calculation, but it underlies lots and lots of useful things in the real world. We had the radar example last time. You can think of more complicated situations in which there's a bunch or lots of different hypotheses about the environment. Given any particular setting in the environment, you have a measuring device that can produce many different outcomes. And you observe the final outcome of out of your measuring device, and you're trying to guess which particular branch occurred. That is, you're trying to guess the state of the world based on a particular measurement. That's what inference is all about. So
the inference thing, it's kind of like, yeah, you have kind of like big tree like this. And so you have that a particular outcome occurred. So your reading is kind of here and here and here and here and here. And you're trying to figure out which branch was most likely.
World problems only differ from the simple example that we saw last time, in that this kind of tree is a little more complicated. You might have infinitely many possible outcomes here and so on. So the setting up the model may be more elaborate, but the basic calculation that's done based on the Bayes rule is essentially the same as the one that we saw. Now, something that we discussed is that sometimes we use conditional probabilities to describe models. And let's do this by looking at a model where we toss a coin 3 times. And how do we use conditional probabilities to describe the situation? So we have one experiment, but that one experiment consists of 3 consecutive coin tosses. So the outcomes, the possible outcomes, our sample space consists of strings of length 3 that tell us whether we had heads, tails, and in what sequence. So 3 heads in a row is one particular outcome. So what is the meaning of those labels in front of the branches? So this P here, of course, stands for the probability that the first toss resulted in heads. And let me use this notation to denote that the first toss was heads. I put a H in toss 1. How about the meaning of this probability here? Well, the meaning of this probability is a condition.
This outcome occurred. Probability H1 equal to the probability of, it's basically, I guess, H1 like this. If in your original experiment, you basically had like H1 or T1, and it was either this thing or this thing happened. Yeah. I'm a little confused. Does this have its own sample space? No, I guess the only kind of sample space that we're dealing with is yeah, it's basically this HHH thing. Yeah, this HHT, and okay, yeah, this like probability of H1 thing here. This is actually basically equal to the probability of, it's like a set of things where that first thing was head. So you have these, you have all these outcomes. Yeah, HHT, HTH, HTT, like this. This is H1. It's this set here. Yeah, you kind of always have to start with your experiment and like define your sample space. And then when you see a kind of event, you say, okay, that's a set of outcomes. All right, what set of outcomes is that? It's kind of weird to think about it like this, though. It's not as intuitive. When you just kind of like look at like the probability of H1, I don't know, you kind of like lose the connection to the ultimate sample space, and you just kind of start intuiting like, oh, it's the probability of, yeah, probability of a coin flip. I don't know.
Of this probability here? Well, the meaning of this probability is a conditional one. It's the conditional probability that the second toss resulted in heads, given that the first one resulted in heads.
I guess, yeah, if you're drawing this out, then you literally have the probability of H2 given H1 is equal to, well, what is H2? I mean, it's a set of outcomes. So it's the second one is heads. So you have like heads, heads, heads. You have like heads, heads, tails. You have tails, heads, heads. You have tails, heads, tails, like this. So it's this thing given, yeah, the first one is heads. Heads, heads, heads. Heads, heads, tails. Heads, tails, heads. Heads, tails, tails. And to kind of draw it out a little bit more, it's like, I guess we could kind of draw out all of them, and we could say that the sample space is heads, 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 it's tails, heads, heads, it's tails, 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 heads, heads, tails, tails, heads, tails, tails, tails. 2, 3, 4, 5, 6, 7, 8. And so this is kind of like our sample space here. And so when we say the probability of H2 given H1, we're saying that H1 occurred. So H1 occurred. So H1 is like this, and this, and this, and this. Okay, so it's like we're kind of in this zone right here. And now what's H2? H2 is, the second one was heads. So H2 is like this, and this, and this, and this. So just kind of like looking at the definition or whatever, we're kind of like in this, region here. It's like the probability of is equal to, we're in the H1 universe, and then we're looking at the intersection of H2 intersected with H1. Yeah. If we wanted to do it out like Bayes' rule, I guess.
And similarly, this label here corresponds to the probability that the third toss resulted in heads, given that the first one and the second one resulted in heads. So in this particular model that
So given that the outcome is in one of these, what's the probability of this event occurring?
wrote down here, those probabilities P of obtaining heads remain the same no matter what happened in the previous toss. For example, even if the first toss was tails, we still have the same probability P that the second one is heads, given that the first one was tails. So we're assuming that no matter what happened in the first toss, the second toss will still have a conditional probability equal to P. So that conditional probability does not depend on what happened in the first toss. And we'll see that this is a very special situation, and that's really the concept of independence that we're going to introduce shortly. But before we get to independence, let's practice once more the three skills that we covered last time on this example. So first skill was multiplication rule. How do you find the probability of several things happening? That is the probability that we have tails followed by heads followed by tails. So here we're talking about this particular outcome here, tails followed by heads followed by tails. And the way we calculate such a probability is by multiplying conditional probabilities along the path that takes us to this outcome. And so these conditional probabilities are recorded here. So it's going to be 1 minus P times 1 minus P. So this is the multiplication rule. Second question is, how do we find the probability of a mildly complicated event? So the event of interest here that I wrote down is the probability that in the three tosses we had a total of one head, exactly one head. This is an event that can happen in multiple ways. It happens here.
So it's like the probability of one head. So this is an event, it's a set of outcomes, which is equal to the probability of one head. I guess we have heads, tails, 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 heads, tails, and we have tails, tails, heads. What's the probability of this event? I mean, you always have at the probability of an event. You can always break up the event into disjoint sets. So you can say it's the probability of. Well, I mean, you can just always do this by set theory, like heads, tails, tails, union, tails, heads, tails, union, tails, tails, heads. And yeah, if we're like taking the probability and we're unioning disjoint sets, this is just the probability of heads, tails, tails, plus probability of tails, heads, tails, plus probability of tails, tails, heads. Yeah.
It happens here, and it also happens here. So we want to
Wait,
find
what? There was no way. No, there should only be three. I can't read this other one. This would be tails, heads, tails, heads, heads, tails, heads, tails. This would be good. This would be tails, heads, heads. This one's not.
total probability of the event consisting of these three outcomes. What do? We just add the probabilities of each individual outcome. How do we find the probability of an individual outcome? Well, that's what we just did. Now, notice that this outcome has probability p times 1 minus p squared. That one should not be there. So where is it? It's this one. Okay. So the probability of this outcome is 1 minus p times 1 minus p, the same probability. And finally, this one is again 1 minus p squared times p. So this event of one head can happen in three ways, and each one of those three ways has the same probability of occurring, and this is the answer. And finally, the last thing that we learned how to do is to use the Bayes rule to make an inference. So somebody tells you that there was exactly one head in your three tosses. What is the probability that the first toss resulted in heads? Okay, I guess you can guess the answer here. If I tell you that there were three tosses, one of them was heads, where was that head? In the first, the second, or tosses? First head to make an.
Given that there was one head, the first toss is a head. So we have one head. So the probability of first toss is head given one head. So these are events, sets of outcomes. So the probability that the first toss is a head. This would be head, 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 tail, head, tail, head, head, tail, tail. Given you just had one head. The one head is head, tail, 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 head, tail, 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 head.
Inference. So somebody tells you that there was exact one head in your three tosses. What is the probability that the first toss resulted in heads? Okay, I guess you can guess the answer here. If I tell you that there were three tosses, one of them was heads, where was that head? First, the second, or the third? Well, by symmetry, they should all be equally likely. So there should be probability just 1/3 that head occurred in the first toss. Let's check our intuition using the definitions. So definition of conditional probability tells us the probability of the conditional probability is the probability of both things happening. First toss is heads, and we have exactly one head divided by the probability of one head.
So this is like, so the first toss is head and one head. The intersection of those two. The first toss is the head, is the first toss. Head, head, head. Intersected with one head. The intersection, so the first toss is, it's basically just this. It's just equal to head, tail, tail. Over one head. Probability of one head. Head, tail, tail. It's just one over it.
What is the probability that the first toss is heads and we have exactly one head? This is the same as the event heads, tails, tails. If I tell you that the first is heads and there's only one head, it means that the others are tails. So this is the probability of heads, tails, tails, divided by the probability of one head. And we know all these quantities. Probability of heads, tails, tails is p1 minus p squared. Probability of one head is 3 times p1 minus p squared. So the final answer is 1/3, which is what you should have guessed on intuitive grounds. Very good. So we got our practice on the material that we did cover last time. Again, think there's basically 3 basic skills that we're practicing and exercising here. In problems, quizzes, and in real life, you may have to apply those 3 skills in somewhat more complicated settings, but in the end, that's what it boils down to usually. Now, let's focus on this special feature of this particular model that I discussed a little bit earlier. Think of the event heads in the second toss. If I tell initially the probability of heads in the second toss, you know that it's P, the probability of success of your coin.
It's so weird that like there's such a mismatch between the intuition of like heads in the second toss. It's like you just very much think like, oh yeah, you toss a coin and it comes up heads and it's like 50-50 or like P or whatever. But if you write down, if you say like the event heads comes up in the second toss, that's like not similar to that at all. It's like a set of outcomes. I guess you're thinking of like all the different, and so now you're not thinking of just one toss. You're thinking of all 3 tosses, and you're thinking of all the different outcomes of those 3 tosses where there was a head in the second toss. And like that's the event H2.
If I tell you that the first toss resulted in heads, what's the probability that the second toss is heads? It's again P. If I tell you that the first toss was probability that the second toss is...
And it's so weird, like to look at this, you would just think, oh, it's like, you would think it's kind of like the sequence in the experiment, like the partial results. You'd say, oh, like the, the first one came up heads, and now what's the probability of the second one? That's like the very intuitive way. But if you just kind of like look at this and expand out what these terms actually are, it's very different. It's like, given that we're in a scenario where the first one was heads, so we're just kind of like looking at a bunch of different options of what happened, and now we're saying, okay, what's the probability that yeah, you're kind of given like a set of things that are fixed that like are possible, and now what's the probability that the second one was heads? That yeah, it's kind of like here's all these like outcomes which we know are in contention. Here are the ones which would make this thing true, and now we're like we're kind of doing this union, this intersection of the two, basically. Very different way to think of it. Very different way.
It's again P. If I tell you that the first toss was tails, what's the probability that the second toss is heads? It's again P. So whether I tell you the result of the first toss or I don't tell you, it doesn't really make any difference to you. You will always say the probability of heads in the second toss is going to be P, no matter what happened in the first toss. This is
like every time I've gone through this class, I think this is probably where I get really stuck. It's like I don't really have like a rigorous like understanding of what these terms actually are. So it starts getting like more abstract, and I kind of lose. I just kind of like eventually I can't really follow anything. Can't really follow everything anymore because it becomes, it just becomes too abstract. But kind of like really just like knowing, all right, what is this term? What does it expand to? Let's just do out the full calculation. Can like always fall back to that if intuition like fails. At least that's my hope.
Situation to which we're going to give a name, and we're going to call that property independence. Basically, independence between two things stands for the fact that the first thing, whether it occurred or not.
And this is even a thing, like this is like really when you're even doing, when you're doing conditional probability, like this both A and B, these are both within the same, like this is the same probabilistic experiment, and like these are just two events within that sample space. It's like one experiment. It's not like multiple ones. It's not like B was like the first experiment and now like A is the second experiment. It's not that when you kind of like just actually do out the definition and you're rigorous about it. It's just it's like one experiment that happened. Yeah, it's kind of weird and awkward that we're kind of like, I don't know, if you have like two dice and you have like 1 and 3, you really do want to say this is like two experiments because it's like, oh, here's like the first die roll and here's the second die roll. But it's not really the case. It's just like one experiment. This is the outcome of the experiment, and like you're done. Now, I feel like in the real world where you have like some repeating process where like things never end and it's just one thing after the other. Yeah, I don't know how you kind of like be more rigorous about that. I don't know. Maybe there's a way to think of them as separate experiments. I don't know. We'll see.
Doesn't give you any information, does not cause you to change your beliefs about the second event. This is the intuition. Let's try to translate this into mathematics. We have two events, and we're going to say that they're independent if your initial beliefs about B are not going to change if I tell you that A occurred. So you believe something, how likely B is, then somebody comes and tells you, A has happened. Are you going to change your beliefs? No, I'm not going to change them. Whenever you are in such a situation, then you say that the two events are independent. Intuitively, the fact that A...
All right, that's cool. We'll pick this up next time. See you guys later. Peace.